Our speaker today is Dr. Donald Robertson. He's currently on a Newman Fellowship in Pure Maths within the Department of Mathematics at the University of Manchester.
This is a talk about dynamics in polygons. It sort of fits into, well, dynamical systems, which is a part of maths that cuts across pure and applied maths. What I will talk about today is maybe mainly pure maths, but is also of interest sometimes to people who are doing some things related to physics, although I won't go into that part of it too much. So what are we talking about? Sometimes people call it billiards. So we're going to fix a polygon in the plane. I've drawn one there in black, just a 5-sided polygon. And we're going to essentially watch as a billiard ball or a snooker ball or a pool ball, whatever game you're used to, bounces around in this table. So more precisely, we're going to fix a location, that's the red dot, and also a direction, that's the red arrow, in which this pool ball or billiard ball, whatever, is going to start moving, just as if you struck it with a cue. There's only one ball, so it's not a complicated game like pool or anything like that. And so the ball will start moving in that direction. And eventually, of course, it will hit the edge of the table. It will hit one of the black lines, one of the sides of our polygon that we've fixed. And we have a specific rule about how to proceed with the trajectory of the billiard. When we hit edge, we say that we have to preserve angles. So if you remember where we started, we soon hit the left edge of the board and we reflected off that side so that, you know, as you would say in optics or whatever, the angle of incidence was equal to the angle of reflection. Those two angles there are supposed to be the same, although it's not a great drawing. And then you keep going again in a straight line, just as a pool ball would. There's no spin or anything like that. And so then you travel along for a while. We hit this sort of bottom right edge, and then again we bounce off it with angle of incidence equal to angle of reflection. Those two angles are the same with the double marks. And so on. We keep going like this forever. We don't assume that there's any friction or anything like that. So you just keep going. This trajectory, this billiard ball bounces around without ever slowing down or speeding up or all of a sudden changing direction. It will only change direction if you bounce off an edge and things like that. Now you might be slightly worried about what happens if you hit a corner of the polygon. There's 5 of them in this case. That's pretty unlikely, but if it does happen, we just stop. We're not going to bother with having a complicated reflection rule for when you hit a pocket or a corner. We just don't worry about that. Although I've drawn maybe it's worth saying, I mean, when you play snooker or pool or whatever in real life, the ball is, you know, it has some radius, it's has some size, but we're just thinking about a sort of idealized point particle bouncing around here. So it's not like this thing has a radius. It's just traveling on lines. Okay, and then so we keep going. There's a third bounce there. So this is an example of a dynamical system. You start with some initial conditions, in this case, the location and the direction in which you're going to start from. And then you have a rule for evolution, a rule for moving around, a rule for how trajectories develop. And that's what I just sort of tried to explain to you. You travel in a straight line and then you reflect off the sides in a natural way with the two angles being the same. And so now we have, well, hopefully maybe some interesting questions to ask. And broadly speaking, because we're doing, or because I'm talking about dynamics, then we ask something like, what happens to these trajectories in the long term? If I watch them for a very long time, if I watch this ball bounce around and around and around for days or years or centuries, am I going to notice anything? More specifically, so here are some questions that one might ask. Are there any periodic trajectories, first of all? So a trajectory is periodic if after some amount of time you end up exactly where you started. Now for our billiards, that doesn't just mean that the ball has returned to the position where it started from, but also that it's going to continue traveling in the same direction as it was traveling initially. Because you can imagine that if the ball started in this direction, you might at some point end up with the situation traveling where the ball is traveling like that. Sorry, let me do it in front, like that. So that would not constitute a periodic trajectory necessarily, because you didn't get back to where you started in terms of the direction that you're traveling in. But if you get back to where you started and you're about to travel in exactly the same direction, we'll call that a periodic trajectory. Are there any? So that's sort of the first question. These are maybe simple trajectories in some sense, because if you watch them for a long time, they're just going to repeat and repeat and repeat, bouncing around the exact same path on the table inside the polygon. So that's a nice question to think about. On the other hand, you could ask whether there are trajectories that are dense in the polygon. So that's maybe almost the opposite behavior. It might be the case that you strike the ball and it starts bouncing around and it will sort of go everywhere. If you wait long enough, it will get as close as you like to any position whatsoever in the table and with any prescribed direction as well. Such a trajectory maybe is not understandable in some sense because it has to go everywhere. It has to be very maybe chaotic, you could say, I suppose. It has to eventually get very close to every location. And then a more refined question than the second one is the third one. Let's ask, for instance, what proportion of time, so let's say I've been watching this billiard bounce around for an hour, for how much of the hour was the billiard in the bottom half of the table? I mean, bottom half, whatever you want to mean by that. Just fix some region inside the polygon and sort of keep track of the moments, the seconds, where the billiard happened to be inside that region that you picked. Does it spend most of its time there, hardly any of its time there, the correct amount of its time there, whatever that means to you? So these are sort of some examples of dynamical questions that we could ask about any dynamical system. Today, we're mainly going to talk about the first question, and we're mainly going to talk about billiards and polygons, but that's sort of a general collection of questions that you'll find in many dynamical systems problems. Okay, but so before I go, just a quick word about sort of other things. I'm talking today about polygons, and there are lots of polygons, but you could work with boards which are not polygons. So there's a relatively famous one called the Bonimovich Stadium, where this is just a cartoon, but it's supposed to be a rectangle with semicircles on either side. And you play the same game, angle of incidence equals angle of reflection as you bounce around, and here's a toy trajectory inside that. But as I'm saying here, so for now, we're just going to talk about triangles and squares. So let's keep it a bit simple for the beginning. So if you're curious about this, if you Google Bonimovich Stadium, there's nice articles about that. And I've got some links at the end if you're curious. Okay, so let's start with maybe the simplest table that you can imagine, the unit square. So this is just a square of side length 1. The width and the height is 1. And I'm going to start at this blue dot and head off in this sort of northeasterly direction. So the blue is the trajectory, sort of the history of where my billiard ball has been. And just at the moment, in the snapshot that is this cartoon picture here, it happens to be where the red dot is, and it's going to continue in that way. So you can see every time it hits the edge, every time it hits an edge of the square, you've got angle of incidence equals angle of reflection, at least to the extent that I'm able to draw that. And you can predict, I mean, you could keep drawing this yourself, and you'd know exactly how things are going to progress. how can we analyze this? How can we try to answer maybe the first question anyway? Is this, if I keep drawing this trajectory, is it going to come back to where it started, or is it going to do something else? Is it ever going to come back to where it started? And because we're in the very special situation of the square, there's a nice little analysis we can do here, just sort of as follows. So no matter what direction you're going in, provided it's not vertical, but never mind about that just now, you're going to return at some point to the same height and direction as when you started. Because let's say if you first bounce off the top, as in this picture, then, excuse me, you'll come back to the same height, but you'll be going in sort of the wrong direction, and then you'll bounce off the bottom and travel up again, and at some point you'll be at the same height and sort of in the same direction, still in that northeasterly direction. And let's call the horizontal distance that you've traveled in that time, let's just say it's alpha. And so one thing that you can check is that whether alpha is rational or irrational will tell you whether this blue trajectory is ever going to come back to where it started or not. So in that case, there's a very, I mean, you have to think about that a little bit, and we can talk about that more at the end if you want, if anyone wants. But it's kind of a nice result. So you calculate this explicit number alpha, which is also related to the slope. If you prefer to think about the slope or the direction in which you're going in the beginning, you can get alpha from that and vice versa. But in any case, you can calculate this number alpha, and you just ask yourself, is this rational? If it is, then you're definitely going to have a periodic trajectory after maybe a long time. It might take a while, but eventually this little red arrow thing will be exactly back at the start where you began the whole thing. And that's sort of the story for squares. If alpha is not rational, if it's irrational, like square root 2 or pi or whatever you like, then sort of exactly the opposite thing will happen. This little red dot will never come back to where you started, and it will get as close as you like to every other location in the square. So in other words, we'll have a dense trajectory. And in fact, although this is harder to explain, it will spend the correct amount of time in any part of the square that you could think about. For instance, half of its time will be in the bottom of the square, a quarter of its time will be in the top right quarter of the square, and so on. Okay, so maybe that's enough time looking at this picture of a square. It's a little bit more interesting to talk about triangles. So as a sort of what seems at first to be a digression, let me tell you about this old problem. So Fagnano, I think maybe an Italian mathematician, asked this question maybe at the end of the 19th century or something like that. So you start with an acute triangle. I've drawn one here in black. And you ask the question, or Fagnano asks the question, sorry, excuse me. Amongst all the inscribed triangles, which one has the smallest perimeter? So an inscribed triangle is just one whose vertices are lying on the original black triangle you started with. So the red triangle and the blue triangle I've drawn here, these are inscribed in the black triangle because their vertices are sitting on the edges, somewhere on the edges of the black triangle. And so there's thousands and millions and trillions of them because you can move along this edge, that edge, or the other edge of the black triangle. And so amongst all of these, you know, it's a cute question to ask. Which one has the smallest perimeter? Which one has the property that the sum of its three sides is minimized? Who knows? Fagnano answered this question using calculus. So you can use calculus to answer interesting questions sometimes. But the answer sort of is by itself very nice. So here's the answer which Fagnano gave. There may actually have been two Fagnanos, a father and a son, and I'm not sure exactly of the history, but anyway, there's a very specific triangle which comes from a geometric construction which answers the question. It happens to have a name. It's called the Orthic Triangle. Don't know what that means, but anyway, it's the triangle whose vertices are the feet of the altitudes. So you start with, again, the black triangle that you're interested in, and then you draw its three altitudes. The altitude of a triangle is each vertex of the black triangle has an altitude. The altitude is the line from the vertex to the opposite side that meets the opposite side perpendicularly. So the three red lines here are the three altitudes of the black triangle. They happen to intersect at a common point. That's a nice little fact by itself. But anyway, if you join together the feet of those altitudes, you get an inscribed triangle. That's the Orthic Triangle. And it turns out that this triangle has the smallest perimeter of all inscribed triangles that you could possibly write down. So that's what Fagnano did. Why am I mentioning this? Well, maybe it's sort of obvious, but it turns out that the Orthic Triangle is a billiard trajectory. In other words, where the Orthic Triangle meets the sides of the original triangle, you have equal angles at all three of its vertices. So I've drawn these sort of equal angle symbols at the three vertices of the blue triangle. That means that if you place your billiard ball on the blue triangle and you strike it in the direction of whichever edge of the blue triangle you're on, then it will bounce once, bounce twice, bounce a third time, and come back exactly to where you started. So I think that's kind of amazing. First of all, this Orthic triangle is easy to draw. If I give you a specific triangle, you draw the altitudes and then you draw the triangle. Secondly, it came about, or at least was known to solve this other problem about the minimal perimeter of an inscribed triangle. And thirdly, just the fact that these angles are the same. That's kind of amazing by itself. So because these angles are the same, as I said, we do have a periodic trajectory for the billiard inside the triangle that we that we started with. So in some sense, we've answered our question. We have found periodic trajectories for billiards in triangles. I don't know if I said it. I should have. I wrote it down, but anyway. In Fagnano's question started with an acute triangle. So all of the interior angles are less than 90 degrees. What happens if you don't have an acute triangle? Let's say you have an obtuse triangle, so there is an angle of more than 90 degrees. You can still play billiards inside such a triangle. There's no reason not to. And you can even construct still the Orthic Triangle. That's the blue triangle shown in this picture here. But it's not inside our original black triangle anymore, because the altitudes from two of the vertices, the altitudes from the acute vertices, are not inside the original triangle. So two of the vertices of the Orthic Triangle, where the feet, where the altitudes meet the sides, which you have to extend in this case, are not inside the original triangle. And so if you tried to do the same thing, start your billiard ball rolling on the blue line inside the original triangle in the right direction, you would hit an edge and you would bounce off. But then you're not following the orthic triangle anymore, because the orthic triangle has gone outside the triangle and is going off over there, up to the top right or up to the top left. And it's they've become disjoint now. You can't understand one in terms of the other. And so this orthic triangle business doesn't work in obtuse triangles for this reason. So it only works for acute triangles. And amazingly, somehow, because it seems like a relatively straightforward problem, nobody knows whether every triangle has a periodic billiard trajectory. So this very nice question, which I think hopefully I've explained sufficiently well that you agree you could explain it to anybody. No, it has an answer that we don't know. There might be this very mysterious triangle out there, this mysterious obtuse triangle that just happens not to have a periodic billiard trajectory, a specific place and a specific direction in which, if you strike the cue ball, you'll never come back to where you started. I don't know if anyone believes that such a thing is possible. I hope it's not, but that's just my feeling about this question. Maybe you disagree, and I'd like to hear about that. But the fact is that nobody has a proof either way. Nobody's been able to construct a specific triangle that does not have a periodic trajectory, and nobody's been able to prove that every triangle does have a periodic trajectory. There has been some work on this problem. For instance, if your obtuse angle is less than 100 degrees, I think there's a computer-assisted proof that you always have a periodic billiard trajectory. But in general, the question is open. Kind of amazing. Okay, so next I'd like to talk about another, well, a special class of triangles, where it turns out that we can still solve the problem whether they're obtuse or not. So let's agree that a triangle is rational if all of its angles is a rational multiple of pi. So pi over 2 or pi over 8. Anyway, here's a picture of one. It's got a right angle. Over 2, it's got a pi over 8 and a 3 pi over 8. This one I've drawn is a right triangle, so it's not acute. Right triangles don't really have orthic triangles. Anyway, you cannot construct a periodic billiard trajectory by the orthic triangle business if you have a right angle. So from what I've told you so far, we don't know whether this triangle has a periodic billiard or not. Oh, okay, well, I told you that somebody proved it, but apart from that, we don't know why that's the case. So there's a sort of a new game that you can play. This is called unfolding, which I would like to explain to you now because it's very, very nice, I think. So here's the idea. I'm going to start with my triangle. I've drawn one here. And I'm going to reflect a copy of it across the vertical edge. So I'll show you on the next slide what I mean by that. But what you should expect is that after this procedure, we're going to have two triangles side by side, the original triangle and its reflection in the vertical edge. So we'll end up with a picture sort of like this. Okay, so that's two triangles. Get rid of that. That's two triangles. We've reflected one across, we've reflected itself across the edge. And then we're going to keep going. We're going to do this again. We're going to unfold another little copy of this triangle across the northeasterly edge, like so. And so we've got a third one going around here. And we're going to keep going, unfolding and unfolding and unfolding around this, well, what is developing into a sort of central vertex until we get back to where we started. We will get back to where we started because every time we do an unfolding, we add an additional pi/8 of angle around what will sort of become the middle here. And so if we do this totally 16 times, if we unfold and unfold and unfold and unfold until we've done it 16 times, we'll have 60, well, we've unfolded 15 times. We'll have 16 sort of copies of our original triangle, all fitting together nicely around that central, that central vertex. The result of doing that is an octagon. So I couldn't draw this by hand, I had to do this on the computer, but hopefully you can see sort of the two triangles in the middle at the top would be those two triangles. So these two triangles are somewhere in this picture, they're in the top middle. And then we went all the way around this sort of center of the octagon, unfolding and unfolding until, as I said, we got 16 triangles sitting around the central thing. So that's an octagon. The sides are all of the same length because each side is made up of twice the specific side of the original triangle that we started with. And the angles in the middle are all the same. So it's a nice regular octagon. So I want to tell you about a different type of dynamics that we're going to play on this octagon, and then relate this back to periodic billiard trajectories on our original triangle. So what dynamics are we going to play on the octagon? We're going to start with the same information, a specific location and a direction in which to travel. And we're going to go in a straight line, just as a billiard ball would. But now, instead of bouncing when we reflect an edge, which is what we were doing in the billiard case, we're going to do something entirely different. So when this ball hits the edge, it's going to disappear and magically reappear at the same location on sort of the opposite side of the octagon. So here's what I mean by that. So here in blue is some of the trajectory, some of the history of this red particle. So if you remember where we started, it was traveling northeasterly for a while. It got to the edge. It hit one of the edges of the octagon. And then it magically reappeared sort of on the corresponding opposite edge in the same distance along. So it essentially tunneled vertically instantly to the bottom of the octagon, and then it kept going in that same northwesterly direction. So unlike with the billiards, there's no change of direction here. You're always going northeasterly. You're always going northeasterly. The only thing that happens is that you do this magical tunneling, this magical transportation or identification when you hit an edge. Notice in the octagon that every edge has sort of an opposite, which is parallel to it and of the same width. So you could, no matter which edge you hit, there's a friendly edge that you'll reappear on when you do this tunneling. So here this thing has tunneled twice, and now here it is a little bit more. It hit the top once more, and then it was so far to the right that next time it went northeasterly, it hit this northeastern edge of the octagon, and then so it reappeared in the southwestern edge. And it kept going northeasterly because you never change direction in this type of dynamics. It's not a billiard dynamics. I'm going to call it a straight line dynamics. But anyway, and you can see you got kind of close to where you started, but not exactly where you started, just as it happens. Okay, so that's the straight line dynamics on the octagon. Just, I'll say it again, when you hit an edge, you reappear at the opposite edge. This is a dynamical system, so we can ask the same questions. We had a list of questions in the beginning that one could ask about any dynamical system. So does this octagon have, does the straight line dynamics on the octagon have, for instance, periodic trajectories? Yes. So here's a same octagon, just a slightly different picture. I've brought back the triangles from before. I've shaded one of them in. Never mind about that just now. The blue line is a straight line flow trajectory. It's going straight north. So if you place your billiard on the blue line and you travel straight north, well, you'll go north until you hit the top edge. You'll be magically transported to the bottom edge without moving left or right, because you always sort of don't move further along the edge when you're transported. And then so when you continue going north, you'll go back along this blue line again, and you'll just loop sort of around and around and around and around. You know, a little bit like maybe in asteroids or something like that. So this is for the straight line flow. This is a periodic trajectory. Now here's where this sort of amazing thing happens. The octagon came from unfolding a triangle that we were interested in. We wanted to know about the billiard trajectories. We wanted to know about periodic billiard trajectories in that triangle. So we unfolded it. We got an octagon. Now we're looking at this other dynamics, the straight line dynamics on the octagon. We found a periodic trajectory for the straight line dynamics on the octagon. We can now sort of fold everything up again. And it turns out that what we're going to get is the following. So now let's focus on this gray triangle, the triangle I shaded in. It's not the one we started with when we did the unfolding, but that doesn't really matter. They're all sort of the same triangle. So let's start with the blue trajectory at the bottom of the gray triangle. We can, and going north. So now we can do two things at once. We can think either about the billiard trajectory inside the gray triangle, or we can think about the straight line trajectory in the octagon as a whole. Because the octagon was obtained by unfolding, when this straight line trajectory continues into the triangle adjacent to our gray triangle that we're interested in, the billiard trajectory that we get when we have to reflect is just the blue line reflected back into the gray triangle. So this, if we watch this blue trajectory, it leaves the gray triangle and continues going north. If we take that line segment that's inside that white triangle and we fold it over again back into the gray triangle like this, then that's exactly what the billiard is going to do. Because when you reflect, you preserve the angles in the correct way. So this second blue segment in the gray triangle is the reflection of the blue segment in the adjacent white triangle. And that blue segment in the adjacent white triangle is part of the periodic trajectory on the octagon. We've just sort of, in this refolding sort of procedure, we're now seeing what that has to do with billiard trajectories. So, okay, that didn't cause any major disasters. Let's continue. As we keep going north on the straight line flow, we're going to enter into a third triangle, the next white triangle. That too contributes to the continuation of the billiard trajectory. Once we fold that back into the gray triangle, then it's going to continue to do whatever it does. It's becoming harder to see exactly how you would draw it, but so I had the computer do this. But you know, if you do it carefully, then this is what's going to happen. And now here's where sort of the amazing thing happens. When we continue again into the third white triangle, we can also reflect that into the gray triangle. But notice that this time, sorry, when the blue straight line trajectory leaves the third white triangle, it does so at right angles to the edge. And so, oops, the fourth segment of the billiard trajectory will meet the edge of the gray triangle at right angles as well. Which means that because when the billiard comes off again, it has angle of incidence equal to angle of reflection, it's going to go straight into the cushion and then straight out again. And we'll just repeat backwards the original thing that we've spent now some time drawing. So there's sort of no more picture for that, but I hope you can imagine that this billiard trajectory, which started at the bottom of the gray triangle where the blue line meets the bottom, will bounce, 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 and then bounce straight back as it goes through the fourth white triangle, back from the fifth white triangle, back again to the sixth white triangle, and then finally back to where it started through the seventh white triangle, which is also finally when the original straight line flow comes back to where it started. They have to agree at the end of the day because of how they're related like this. So in this way, by doing this ingenious unfolding procedure and getting an octagon where it's easy to identify a periodic trajectory, we can fold that back in on itself to get a billiard periodic trajectory. So that's what I just said here. We found a periodic billiard trajectory in the pi over 2, pi over 8, 3 pi over 8 triangle. That's the triangle we've been talking about. By unfolding to an octagon, finding a periodic straight line trajectory, and then refolding it. That's what we were doing at the end. And so we got a periodic trajectory. There's a question here from Ricardo. You have infinite periodic trajectories. Yes, that's right, because this blue vertical line that we started with is just one of many periodic straight line trajectories on the octagon. You could nudge it to the right or to the left, and that would give you more. But you could do something also more interesting. You could take a northeasterly trajectory, doing something like that. And there are ones which are more complicated as well that sort of wind around in a more complicated way on the octagon before they come back to each other. But yes, even by nudging the blue line left or right, you get already uncountably many periodic trajectories on the gray triangle. So there's a lot of them, far more than we ever imagined, perhaps. I mean, the Orthic Triangle in the previous case was only one. Okay, so I just like doing this, so let's do that again. There's the periodic trajectory. So that's what we did, this unfolding and refolding. So it turns out to be a theorem, this unfolding procedure that we carried out for a very specific triangle, the right triangle with the pi over 8 angle. You can do that for any polygon, I mean, it doesn't have to be a triangle, whose interior angles are, oh, well, sorry. So what I've written here is about triangles. So every rational triangle can be unfolded to give a polygon where you can play straight line dynamics. What do you really need to be able to play straight line dynamics? You need to make sure that if you hit an edge, there's a friend edge that you can reappear at. And so formally, that's what's written here. The sides of this unfolded polygon come in pairs of parallel sides, and they have to be of the same length. Now, if you start with there's no requirement here that the triangle be acute. So you can play the same game with an obtuse triangle. So if you happen to have, you have to be pretty lucky, but if you happen to have an obtuse triangle whose angles are all rational multiples of pi, then actually we do have periodic trajectories. That's a very small collection of obtuse triangles compared to all the obtuse triangles in the universe. But it's a very nice argument nevertheless. Moreover, when you do this unfolding, the thing that we need is still true. If you unfold and you can find a periodic trajectory for the straight line dynamics, Then when you do the refolding, you'll have a periodic billiard trajectory, which is sort of the argument that we ran through in the special case. You always want to make that work. So this theorem is a very nice construction, the unfolding construction. It doesn't actually tell you whether there are periodic trajectories for the straight line dynamics, though. And that's not obvious. We could see it in the octagon because we drew an explicit, because it was so explicit and so regular and symmetric and nice that we just could notice after thinking about it for a while that if you went straight up, then you'd reappear and it would be a periodic direction. But if you start with some bizarre triangle and you unfold it, it might not be so obvious that there is, in fact, a periodic trajectory for the straight line flow. So that's something that is not easy to prove at all, but has been proved in the 80s, so not that long ago, relatively speaking. Any unfolding of any rational triangle or any rational polygon, more generally, if you want to think about that, does in fact have a periodic trajectory. And it's not at all obvious. So there have been other proofs since then, but this original proof by Maser uses some very heavy technology. There are things called Riemann surfaces. This octagon that we made is secretly a Riemann surface. And then there's something called a moduli space of Riemann surfaces, which is even more complicated. And then you can do dynamics on the moduli space. And by doing dynamics on this complicated thing called the moduli space, Maser is able to guarantee you that, in fact, this unfolding will have a periodic trajectory. And that's it. So thank you for your time.